Nghe thấy em.
Vâng, thì bọn em sẽ lấy dữ liệu từ sàn Binance về ạ. Và dùng model LSTM để dự đoán ạ.
Ừ. Nhưng mà nếu mà chỉ có thế thôi thì khối lượng công việc em thấy như vậy có đủ không? Mình thì đang nghĩ là nếu bài toán chỉ như vậy thì nó khá là đơn giản. Tại vì cơ bản là những cái việc mà price prediction cho Bitcoin mà dùng LSTM thì mình thấy là đâu đó trên GitHub em có tìm thấy hàng tá các cái mã nguồn như vậy rồi. Em có thể
Vâng.
là nói mô tả cách chi tiết hơn là em sẽ làm sâu hơn như thế nào không?
Dạ, bọn em đang nghĩ như thế, nếu mà đơn giản quá thì bọn em sửa lại thêm này ạ.
Ok, mình nghĩ là phải cân nhắc nhé. Tại vì làm sao cái khối lượng công việc nó đủ thách thức, đúng không? Chứ không thể là theo dạng một cái việc tức là cứ ốp một cái mô hình mạng neuron lên rồi tôi test, tôi chạy, tôi predict rồi sau đấy tôi đưa ra cái kết quả được. Đúng không? Nếu mà chúng ta chỉ dừng lại mức đấy như thế thôi thì chúng ta cũng sẽ không học được gì nhiều đâu. Đúng không? LSTM có sẵn hết rồi, code có hết rồi, dữ liệu có hết rồi. Đó. Vấn đề chúng ta phải đặt ra một vài các chỉ tiêu ví dụ liên quan đến hiệu năng, đúng không? Hoặc là những cái gì đấy mà nó thể hiện ra là chúng ta đang làm và chúng ta hiểu rõ và chúng ta có thể làm tốt hơn là gì, phần lớn các cái mã nguồn đang có trên internet chẳng hạn, đúng không? Thì lúc đấy nó mới đáng được nghiên cứu, chứ còn nếu dùng mỗi cái mạng LSTM không với cái bài toán Bitcoin prediction này thì mình nghĩ là bài toán đấy thì tôi có thể làm cái đấy trong vòng 2 tiếng. Với cái việc tức là lên GitHub lấy code về rồi là ok download dữ liệu về train các thứ, nó thật sự là không quá là thách thức với cái bài toán đấy. Rồi mấy bài toán số 2 là Vietnamese Sentimental Analysis. Nhóm số 3 nào, cho tôi ý kiến xem nhóm số 3 định làm gì nào.
Alo, thầy nghe rõ không ạ?
Chào em.
Vâng, thì bọn em định là sẽ chọn một cái dataset ấy, thì bọn em chưa biết là chọn cái nào nó có nhiều bộ ấy. Còn về phần mô hình thì sẽ thử nghiệm các cái mô hình cả cơ bản lẫn phức tạp. Thì ví dụ như mô hình cơ bản thì có thể dùng ANN với cả LSTM, còn
Ừ.
về phức tạp hơn thì có thể ờ, sử dụng cái mô hình như kiểu BERT ấy ạ.
Ừ.
Kiểu Python cái language model xong rồi ấy ra,
Ừ.
hoặc là dùng ensemble learning
Ừ.
cho các cái đấy.
Ok rồi. Cái quan
Thì
trọng đây là mọi người đang muốn là làm các cái thử nghiệm khác nhau, đúng không, trong cái bài toán đấy.
vâng, cơ bản là thế ạ, còn chưa biết thêm cái gì ạ.
Ừ. Ok, thế mình nghĩ là nên nên chọn một cái bộ dữ liệu cụ thể đi, thì sau đấy chúng ta mới có thể so sánh và đánh giá các cái phương pháp đưa ra được. Chứ nếu chỉ
Vâng,
dừng lại cái việc là chạy được trên được cái mô hình và sau đó là test nhưng mà sau đấy cũng không biết đánh giá so sánh như thế nào thì như thế là không nên nhá.
vâng,
Cứ fix một cái bộ dữ liệu đây và sau đó ta tìm cách là đưa ra cái mô hình tốt nhất với cái bộ đấy nha.
vâng, vâng, em
Ok
cảm ơn thầy.
rồi. Với image classification nào, nhóm số 4 nào.
Thưa thầy thì em đã tìm được một cái bộ dữ liệu tức là của Shopee, những cái ảnh sản phẩm của Shopee ấy. Xong rồi
Ừ.
bọn em sẽ thử tìm, tức là xem những cái sản phẩm nào giống nhau dựa trên hình ảnh, nhưng mà tức là sản phẩm giống nhau nhưng mà mức giá khác nhau ở trên hình ảnh thì sẽ phân loại ra dựa trên một đống, rất là cái bộ dữ liệu đấy cũng khá là lớn, ảnh của Shopee.
Tức là như là hình ảnh giống nhau,
Là
giá khác nhau á.
Dạ vâng, tức là nhiều cửa hàng có cùng một cái, nhiều cửa hàng bán cùng một loại sản phẩm nhưng mà giá nó khác nhau, thì mình sẽ đi tách cái sự khác nhau đấy ra.
Nhưng mà về mặt mô hình ở đây thì mình thấy là đó là bài toán gì, nhưng mà vấn đề số lượng các lớp em đã có chưa?
Chưa, bọn em chưa xây dựng cụ thể ạ, mà chỉ mới tìm hiểu về dữ liệu với cả là xem những cái tổng quan về dữ liệu thôi, chứ chưa xây dựng mô hình.
Ok đúng rồi. Ở nhóm tiếp theo này, conditional image generation này, nhóm số 5 này.
Thầy nghe em nói không ạ?
Nghe được em.
Dạ. Thì bọn em cũng chưa biết làm gì lắm, nhưng mà em bây giờ đang định là bọn em đang định là lấy một cái dữ liệu, một cái bộ dữ liệu ảnh, xong rồi có nhãn, sau đó thì dùng những cái mô hình GAN để tạo ra những cái ảnh mới mà cùng nhãn với mấy cái ảnh tức là có những cái nhãn như thế. Thì bọn em định áp dụng vài mô hình gan xong rồi so sánh chúng nó với nhau, có thể là fine tune hoặc là thêm thắt vài cái mới vào.
Ok, rồi. Mời nhóm tiếp theo nào. Nhóm số 9 có đề tài rồi, cũng là conditional image generation. Ok. Nhóm số 9 chia sẻ thêm gì không em? Nhóm số 9 có chia sẻ gì không nhỉ?
Em chào thầy ạ.
Chào em.
Bọn em cũng định thử nghiệm các mô hình như là VAE, Pixel, CNN hay là CRAN, kiểu là sử dụng nhiều mô hình trên một cái bộ dữ liệu để đánh giá coi cái nào tốt hơn.
Ok. Rồi, tức là mình có một gợi ý dành cho các nhóm thế này nhá. Tức là ok, mọi người có thể là về gọi là viết mô tả một cách chi tiết hơn về nội dung mọi người sẽ thực hiện cho cái đồ án đấy, được không? Ví dụ nếu mà viết Bitcoin Privation thì viết chi tiết xem chúng ta sẽ làm những cái gì. Thì mục tiêu là ok để chúng ta có thể lường trước được khối lượng công việc ấy, tránh trường hợp tức là chúng ta có cái báo cáo đồ án nó quá là đơn giản. Em hình dung được không nhỉ? Cái đồ án đơn giản như mình đang hình dung là chỉ là ok là lấy một cái bộ dữ liệu về, đúng không? Lấy một cái mã nguồn đang có, sau ok là train lại và sau đó đưa ra mô hình. Thì đấy là cái việc mà mình đang cho rằng nó là công việc quá là đơn giản. Cái mà chúng ta nên tập trung vào làm là gì? Mọi người xem lại cái bộ slide, có thể có những bài giảng liên quan đến performance tuning ấy mà chúng ta chưa được làm. Thế nhưng mà mình nghĩ là chúng ta sẽ tập trung vào những cái vấn đề như vậy. Thứ nhất là vấn đề liên quan đến gọi là tiền xử lý dữ liệu này, đúng không? Thứ hai là vấn đề liên quan đến gọi là hyperparameter tuning chẳng hạn, đúng không? Thì cái đấy thì mọi người nên tập trung vào. Thứ ba là ok là có thể tập trung vào những cái mô hình mới và sau đó chúng ta tìm hiểu kỹ về cái mô hình đấy và sau đó chúng ta tìm cách cài đặt lại và sau thực nghiệm lại. Đấy, và chúng ta cũng có thể làm công việc liên quan đến so sánh đánh giá. Để tóm lại ý tôi tức là gì? Cái mà chúng ta phải đưa ra cái kết luận với cái đồ án của chúng ta, tức là nó phải là mang thông tin. Nó không thể một cái kết luận đơn giản là trong đồ án này em đã mang cái dữ liệu này ốp vào cái mô hình này và sau đó đây là kết quả của em. Nếu kết quả nó chỉ là đơn giản một cái câu như vậy thì tôi cho rằng đấy là những đồ án rất là đơn giản, quá simple. Mà mọi người nên tập trung vào cái vấn đề tức là ok là gì? Đây là cái vấn đề em nhận được này. Em làm ABC, XYZ rất nhiều các phương án, em làm tiền xử lý, em làm parameter tuning, em làm visualization các thể loại. Và cuối cùng là gì? Đây là các kết luận của em, tức là kết luận đây nó sẽ phải là gì? Liên quan đến cái cách thức là gì? Chọn hyperparameter, cách thức design cái network architecture đấy sao cho nó phù hợp, đúng không? Cách thức làm data preprocessing, rồi cái cách thức mà chúng ta xem xét và đánh giá cái performance trong lúc chúng ta train cái mô hình. Mọi người hiểu ý tưởng ở đây nhỉ? Nha, tôi sẽ có thể tôi nốt lại một vài cái thứ quan trọng mà mọi người cần phải nói ra này. Ok, trong các topic ấy, tôi mới highlight vài ý 1, 2, 3, 4, 5 ấy để mọi người xem nó có thiếu cái ý nào thì mọi người bổ sung thêm nhé. Những ý mình tức là gì? Tránh những cái đề tài theo dạng tức là me too lắm, tức là lấy dữ liệu này ốp vào mô hình này chạy được coi như xong. Mọi người hiểu ý tưởng không nhỉ? Ok không? Hiểu ý tưởng không?
Vâng ạ.
Ok, bây giờ tôi sẽ chia sẻ slide và chúng ta sẽ quay lại cái bài học của chúng ta. Trước là chúng ta đã học qua cái bài là bài học liên quan đến hình như là cái bài performance tuning số 1 rồi đúng không? Chúng ta học cái training neural network part 1 rồi đúng không? Ok, thì bài hôm nay tôi sẽ đảo chương trình một chút và tôi sẽ giới thiệu luôn về cái mạng neuron hồi quy. Tại vì tôi mong muốn là chúng ta sẽ có thể là nắm bắt rất sơ bộ về các cái loại mô hình mạng neuron network phổ biến mà chúng ta có thể sử dụng. Sau đó thì ok, chúng ta sẽ đi sâu vào những cái mạng neuron chuyên biệt cho xử lý ảnh hay là chuyên biệt cho xử lý text, đúng không ạ? Okay, so let's start. Do you see my slide?
Yes.
Okay, so yeah, so for today we will discuss about recurrent neural network, and it is actually the lesson number 9, but I decided to move it to present today so that we can have better understanding on different type of neural network for using on our project. So for today, we will have the following topic. First, about the sequence prediction problem, and then introduction to recurrent neural network, and then we discuss a little bit about the algorithm to optimize the network. It's actually the backpropagation two-time algorithm, and then we discuss about the extension of recurrent network, the LSTM and CRU unit, and then the application of RNN model. Okay. So first, about the sequence prediction problem. So far in the previous class, we have only focused on the prediction problem with fixed sign input and output. For example, in class on image classification problem, we have the input have fixed size. It's actually the image with the particular very specific size, and the output is a fixed number class, right? So my question for today is, what if the input and output are a variable size sequence? It's something we may see in reality, right? For example, in text classification problem, one exam is sentiment classification. We have to categorize the review of a restaurant, a movie, a product, for example, and as the classification would be in two classes, either positive or negative. Okay, so in this case we have a fixed number of output, but the input size is variable, right? So for example, this is the first review. The food was really good. The second review, the vacuum cleaner broke within 2 weeks. The third review, the movie has its own part, but overall it is worth watching, right? So you see, for the input as text review like this one, the second size is different. The first one seems a little bit shorter than the other one, and the last one seems to be the longest one. Okay, so for the inputs that have variable size like this, what feature and classification model should be appropriate to use in order to solve the problem, right? And maybe in other example where we have the outputs at a various size sequence, what would be the model? For example, it's a case of image captioning, where the input is the image and the output would be the title, the caption of the image. Of course, if it is a caption, then it could be any text sequence, right? So in that case, we have fixed size input and variable size output, right? What would be the appropriate model for this problem? Okay, so first we have here a brief review on feed-forward network. And in this network, we actually have the output of the model only rely on the current input, right? And the flow, data flow is like this. We have the inputs, and the input will be fed to the input layer and then go to the hidden layer, and then we got the output of the output layer. It going one way like this, right? And in this feed-forward neural network, of course, we are seeing that they have a fixed structure, so that the input side are fixed, and also the output file as the output side are fixed, right? Like the number of dimension for the input and the number of dimension for the output are fixed. The number of output dimension could be the number of classes, right? And the input side could be the number of feature, right? And by having the input as the output, it really only depends on the current input. Then we are saying that this kind of network have no memory, because it doesn't depend on the order where you fetch the input to the network. The output are always the same, and it's the output are always depend to the current input, right? No notation of order in time. If I change the order of the input, nothing will, change the output, right? For every input, we have the corresponding output, right? So we can say that for the network, if they totally forget the past, they have no relationship between the current input and the historical input, right? So every input, the network treat the input as the independent input, right? For recurrent neural network, we have the collection going from the current layer to the previous layer, for example, and this connection may form a direct cycle in the network architecture. And by having that cycle, we actually have the output becoming rely on the current input, and the output also rely on the recent past historical information. How we are having here the inputs. So we have here the inputs, and okay, so here we have the input, and also the previous hidden states, and the information have the influence to the current hidden state, and then the current output, right? So actually we are seeing here, the output is not only depend on the input, but it's also depend on the previous hidden state, right? So in this case, we have the effect about the memory. The past does not pass away, right? Okay, so for example, about the sentiment classification problem, the food were really good. So this is our text sequence, and we might think about this sequence as a chain of different text token. X is a word, for example, and we can have a network that accepts the sequence. The token in a sequential fashion. Like first we fetch the first token to the network, and then the network learn and it trains the network to be at the hidden state S1, right? And then we fetch the second token to the network, and now the hidden state of the network, the new hidden state of the network will be computed by the second token and also the previous hidden state, right? And now we fetch to the network the third token, and of course the new state will be calculated from the current token and the previous hidden state, and then to the last token, and then we get the final hidden state representation H5, and from that we can apply a small classifier network to predict if the input sequence was positive or negative. And we assume that the final hidden state here and capture the meaning of the entire input sequence, right? So, the network that can implement this kind of, memory context here is actually a recurrent neural network, and the abbreviation is RNN here. So people have been using the recurrent neural network for modeling the language, and they actually build the language model with the RNN. And here we are seeing an example of using the RNN to generate the the text sequence, and the training data for this RNN was from the Bible, right? They fed the entire Bible text into an RNN network and let the model learn about the way the Bible was written, right? About the language model, it's a statistical language model. It's a model that can be described by this probability as a P of the current token when you know about the previous token, right? So for example, in this text generation, the engine can predict a sequence of words one by one, right? And the second of generated word made up the sentence. For example, here is the first sentence that engine can generate, something like here. And also when we have a new seed token, we can generate another sentence, and this is another sentence, right? Okay, so here's about the specific implementation of RNN for learning the language model. And what you are seeing here is actually a character RNN. So in this character RNN, the network is as following. You have this is first token, right? It could be a special token that marks the beginning of the generated sentence. And then for the first token, the input, the output of the current stack is this character, right? it predicts the character, right? So its name is character INN. And then in the next step, the previous predicted token, predicted character, will be used as the input in the next step, right? And now the input is R, and then the model will predict the next output, and the next output is of course compute from the current step and the hidden step of the previous step, right? And now we move to the next step, and of course in this case the previous output will be the input, right? And now we predict the next character, right? So in this case you are seeing that the INN can model the prediction of the next character, right? So if you are going like this to infinitive, then you see infinitive sequence of character, right? Okay, so this is a more clearer description of the character INN. So you have the inputs at a sequence of character, when what you fed to the input is the character, I mean, in a sequential fashion. First you fed the first token, the H. Now you want the model to predict the next character E, and then you fed the E, you want the model to predict the next token L, and then you fed the L, you want the model to predict the next L, and then you fed L, you want the model to predict O, and it actually can generate the word hello. Okay, so for the text H E L L, the model cannot working with the text directly, so you need to find a way to encode the text into a vector, right? And the common way to encode a character or word or text token is using one-hot encoding. The one-hot encoding is very simple. It's like a vector with the size of the dictionary. In the case of character model, it is the number of characters in the language. It's 29, for example. So it have 29 elements, and for each vector, for each token, it have only one single element to be 1 and the other to be 0. It's marked like the index of the token in the dictionary, right? So you add a different vector for different token, and then from that input one-hot encoding, the model can learn the hidden state at each step, and from that hidden state at each step we can apply the softmax function. This is actually the output from the hidden state, and from that we can apply the softmax, right? And we can have a vector that represents the probability of the predicted token. So for example, we are seeing here it predicts the last one, the E, right? And then again the E, we use the one-hot encoding of the E, and then we have a new hidden state, and then it is the output, and from that we apply the softmax function, and we got the probability of the predicted token. In this case we have that 1, 2, 3, 4, that's 4 tokens. So that's why we have this probability of 4 tokens, right? And then this is the probability of the 4 token, and now it's L, right? And now it's oh, okay. Okay, so so in this case we have the model that learn the probability of predicting the sequence E1, E2, En, and it actually the it is sorry, it is multiplication over from I to from I equal 1 to n of probability predict probability of the prediction of EI when we know E1 EI minus 1, right? And sorry, tiếng Việt is tích chập. I just forget the word about the how to call it in English. Let me check the dictionary. Okay, so maybe I will search for it later on. Okay, so let's continue. So here's is another example of having a model that can predict the caption of the photo. Given an image, we must generate a sentence describing the content of the image. So in this example, we have this photo, and then we want to predict the caption. Here the dog is hiding is the caption, right? And we can design a model this way. We have the image, it fed to the CNN in order to learn the embedding of the image, and then when we will start the RNN by using the start token, the special token that to start the generation of the description, and the CNN embedding is fed to the RNN, and then we got the hidden state 0, and then from the start and then hidden state 0 we get the state hidden state 1, and then we use a classifier and we want the model to predict the first token there, and then we use the zeroth token, and then we fed to the RNN again, and we want it predict dog, and then we use the dog to expect the model to predict the next token is ace, and then hiding, right? And then using hiding, and then we fed the hiding again, and we expect the net model to predict the stop token. It's a special token to match the end of the sentence. Right. So in this case, you see we can have the RNN plus the CNN to actually modeling the mapping from the image to the caption, right? Here's another example of RNN in a machine translation. We have the text document in France, for example, and we want to have the the output in English, right? And in that case, we can think about the RNN this way. We have the first RNN that try to, capture the meaning of the sentence, of the short sentence in a latent space, right? It is encoding space, and then from that latent space, we can actually use another NN and then predict the sentence in a new language. Okay, this is in English, and the source sentence was in France. Okay. Okay, so here's the summary of prediction type. Normally we have one-to-one mapping. For example, it's image classification problem. It's a fixed input, and then we have fixed outputs. And in the case of image caption generation, we have a fixed input and a variable sign output. It's one-to-many mapping. And in the case of sentiment analysis, we have variable sign inputs, and we want to predict the class, and it's many-to-one mapping. In the machine translation problem, we have various sign input, and we want to predict a various sign output in another language. And in this case, actually, we may have different RNN for the first part to encode the short sentence, and we may have other RNN to encode the second to decode the second sentence. And this is also many-to-many, but we have the same RNN, and then we predict the output. By using the same RNN, right? And this is still many-to-many, but in different configuration. Okay, so I think that we might take a 5-minute break before we continue. Okay. Okay, so let's continue. Okay, so now we discussed about the recurrent neural network in detail. So here's the architect of an INN. We have the input a step T. It's a XT, and in the NN we have the hidden layer, and for the hidden layer we have two outputs. One output is fed to the next layer. It's actually the classifier, for example, and from that classifier we have the output a step T is a YT, right? Another output of the hidden layer is fed to itself, right? In this case, it is fed to itself, so that we have a recurrent formulation for calculating the new state, hidden state at step T. So the new state at step T actually equal to the the network function, for example. It's calculated from the XT input as time step T and the old state ST minus 1. And that function of W would be the activation plus the multiplication with the weight of the neural network, right? Okay, so that was about the mathematical formulation of calculating the new state of the recurrent neural network. And if we unroll the recurrent neural network, and we are seeing the network would be like this. It is a time step T1. It has the input x1, and the calculation for the hidden state at step 1 could be from the x1 and the first initial hidden state S0, and then we got the first output at step 1, and now we have the we have x2 as time step T2. We got the new hidden state H2 and the new output Y2, and now at step 3, right? And then here we see S3 could be the final state, and we have no more steps, so it would be the final state for the hidden layer. Okay, so of course from this we are seeing that the S3 it calculates from S2 and also from S1. So we might think that the S3 can capture the context of the the input at previous step, x1, x2, right? So for the vanilla implementation of INN, we have the activation function is actually a time function. So the formulation would be HC equal to time W, and the input is XT and hidden state at step T minus 1. And W is the weight of the hidden layer. Right. If you need more information about the vanilla INN, then you might check the following paper from 1990. Okay. So for the time function, this is that a reminder for you about the time function. It has the output in the range from -1 to 1, and for the sigmoid function is from 0 to 1, and it is a formulation for the time function. and it is actually the, I mean, another way to write the time by using the sigmoid function. Okay. And in this slide, you see the derivation of the time, and it is something, I mean, described by itself, 1 minus the time square, right? Okay. So you see that for the function for the formulation of calculating the hidden state at step t, we have the input which consists of two parts, the xt and then the hidden state at step t1. And then in this case, we can reformulate the formulation a little bit to make to break the weight in two parts. Actually, we will write into this way: time ws xt plus ws st minus 1. And we actually want to break the weight into two parts. One part is for the input senior, and the second part is for the pivot hidden state, right? And if you are saying this way, we can, I mean, see it in terms of magic multiplication. So it is a weight for the, sorry, it's a matrix for the weight. It is m. It has the dimension of n and n plus m, right? And for the input to the Rn, we have the vector of n plus m dimension, and the first n dimension is for the input, and the next m dimension is for the hidden state at step t minus 1, right? So yes, so when you do magic multiplication, you are seeing actually the xt will be multiplied to this part, and the st will be multiplied to this part of the matrix, right? Okay, so in the forward pass, we have the st is equal to time w st minus 1, and then if we have the softmax function, and then the et will be softmax of w y st. Wy is the output of the, sorry, is the weight of the output layer, right? And then we can have the at equal to minus log of yt, right? And then this is the Groucho's value for the for the label at input t, right? And this is that's the arrow senior, right? And then we have the arrow senior at another time step, arrow senior at another time step 3, right? And we are seeing that this is a Rn in an undrawn fashion. We actually undrawn the Rn in 3 steps, and we are seeing the network like this, but we can notify that the weight in here, and in here, they are the same, and the weight in here, they are the same, right? Because it is that an undrawn version of Rn, right? Remember that undrawn version of Rn. So if we undrawn it, then that's the replication of the weight here and the replication of the weight here. Okay. Okay. So from that illustration about the sharing weight in the unrolled INN, we can continue with the discussion on the backpropagation algorithm for INN. And here we discuss the backpropagation through-time algorithm, BPTT. And for BPTT, it is the most common method for training INN. The network after unrolling is considered as a large feed-forward network. This is actually a feed-forward network, right? If we don't have the constraint that the weight here is the same as here, right? This is a feed-forward network, all right? And that feed-forward network receives a whole data series as the input. So in that case, the gradient for an INN weight is computed at each of its register in the unfold network. So we can calculate the gradient for the weight in here, the gradient for the weight in here, and the gradient for the weight in here. Right? We calculate the gradient independently, and then we can do a sum or average, and then we use that value to update the network weight, right? So that was the idea about backpropagation through time, right? We can do normal backpropagation, and then we can do a sum and average to merge the update for that specific weight, right? So in practice, we can use a Transcat BPTT algorithm. So in this case, we don't backpropagate for every step, but we can run the INN in the forward direction in K1 time step, and then we can propagate back for only K2 step, right? So the K2 could be smaller than K1, right? So this is a forward path in unrolled INN. This is a sorry, this is a backward path. I missed write the caption for the slide. So here's about backpropagation in INN. We have the arrow as time step t, and it is backpropagate to hidden step t, right? And in order to do this, we do the derivation of e over st, and then we do calculate the derivation of e over w, right? And then derivation of e over st minus 1, right? And of course this will be backpropagate to the earlier step, right? So here's a formulation for calculating the st, so that the derivative is calculated this way. It's okay, so this is a arrow derivative of e over ws equal to derivative of e over st, and then multiply with the this is the derivative of time function, right? And then the hidden state of step t minus 1. Okay, and this is a formulation for calculating the derivative of E over Ws. Okay, and this is the derivative of E over St minus 1. Okay. And so in this case, this is the computation for the derivative of E arrow senior over St minus 1, and this one is calculated with the derivative of E over hidden state of step t, and you are seeing here we have the Ws here, and then this is a derivation of the time function. So in the case that we want to calculate the the arrow senior from the En to Hk, where we have k is too small than n, then we are seeing a big problem. Okay, so let me explain to you. So here's the time function. Yes, it is time function, and this is the derivative of time function. So for time, we have this following property. If we have a last output, and the gradient would be too small because we are at the saturation region, the gradient could be, become 0, right? And for this formulation, we have the observation that if the WH, the weight corresponding to the hidden state, if that weight have, the largest eigenvalue smaller than 1, then in that case we have vanishing gradient. How? This is a brief talk about some improvement for that claim. This is a calculation for the hidden state of step t, right? And let's check with the the activation function is the identity function, right? Let's not think about the time function, but it's the identity function, so that the that function over x equal to x, right? So in that case, we have the derivative of st over st minus 1 equal to ws, because it's an identity function multiplied with the ws, right? And now we consider the gradient of the lost zi on step I with respect to the hidden state xj on some previous step j. That's L equal to I minus z. So z is the previous step and before the step I, right? So in that case, we have the derivation of j I over sj equal to actually the derivation of zi over si and multiply with w h, and it is the power L, right? L is the gap between I and J, right? So in this case, if WH is too small, then a small power by L, then this term will get exponentially problematic when L becomes large, and it could be 0. So in that case, that deviation will become 0. The arrow senior will become 0. So that would Okay, so let me explain again. Okay, so this metric WS can be rewritten with the eigenvalue, right? So let's, in this case, we can rewrite the WS by lambda and Q, and lambda is actually the eigenvalue of WS. So if all the eigenvalue less than 1, then of course this part will become close to 0. And in that case, we are seeing that we might say that the arrow signal from this step cannot affect the layer in the in the previous step, if the gap between that previous step and the current step is too big, right? So somehow the signal from this current cannot be backpropagated to further step in the back, right? Because we get a vanishing gradient problem. Okay, so for other function than the identity function, then you might check the paper, but it say that we only need this condition, the lambda I less than gamma for some gamma dependent on the dimensionality of and sigma. So to be remarked that we can conclude that for a vanilla RNN architecture, the arrow signal from a specific step cannot be backpropagated to further in the back, right? Okay, so here's the test of RNN. The advantages of RNN: it can process any length input. It can compute for the computation for step T can, in theory, use information for many step back. This is in theory, right? But in practice, as I told you, that in this observation, then the arrow signal from a current step cannot be backpropagated too much further in the back, right? The model size doesn't increase for longer input because for longer input we use that unfold the network in that many steps, but the network weight remains the same. Same weight apply on every step, so there is symmetry in how the input are processed, right? The disadvantages of RNN is the recurrent computation is so slow. Because you want to backpropagate the arrow signal to every step in the back, and in some case you have to apply the truncated backpropagation two-time algorithm to make it faster. In practice, difficult to access information from many step back due to the vanishing gradient problem. Okay, so do I have any question about this part? Any question? Hello. Okay, then we can have 5 minute break, then we will continue. Okay, so let's continue. Here we discuss about all the variation of RNN. It's MSTM and ZRU. So for LSTM, it's non-short-term memory. In order to address the gradient vanishing problem in vanilla RNN, the LSTM use specific memory cell to avoid gradient suppression. So here is the the implementation of vanilla RNN cell. You have the T and then the hidden state of step T minus 1 previous step, and then that will be used to calculate the hidden states of step T. And now for the LSTM, we have specific cell to capture the cell state, the cell memory. So the cell state of previous step will be used with the T and then the hidden state of the previous step, and then it outputs the cell state of step T. And the paper that discuss the LSTM you can find in the bottom of the slide. Okay, so now the LSTM cell. For the LSTM cell, you have the following component. First, we have the XT, and then we have the ST minus 1, and then we have ZT equal to 10 WZ from the two input XT and ST minus 1, right? And from that, we can calculate the cell state CT, right? And the CT, you have the connection to its cell, so that the CT is calculated from the previous cell state CT minus 1 plus ZT. Okay, and then the CT will be used to calculate the HT, the hidden state of step T. It is actually HT equal to 10 CT. Okay, and then we have a specific component. Here is called input gate, and for the input gate, it accepts the input XT and ST minus 1, and it has the weight matrix WI, and the ET actually equal to sigmoid WI ET ST minus 1 plus the bias. Okay, and then we combine with the ZT here, right? So that in this case we have the CT. Now the CT equal to CT minus 1 plus IT multiplied with CT. So here we see that IT may be considered as the input gate. Right? The gate will saying that how much the input will be offset to use in order to calculate the hidden state at step T, or in order to calculate the cell state at step T, right? Okay, so you see the IT, it is a sigmoid function over this part, this is the net input part, and you for the sigmoid, you know that for the sigmoid the output could be in the range from 0 to 1, right? So in the case that the IT output 0, then okay, you see in the computation for the cell state CT, there's no current input, right? So in that gate will be closed for the current input, right? So in the case of IT equal to 1, then okay, the computation for CT and ST accepts the input from XT and ST minus 1. Okay. And also here we have the path, the component in the LSTM cell that act as the output gate. For the output gate, they accept the input XT and ST minus 1, and it have the weight matrix WO, and the OT equal to sigmoid, and then this is the net input. And again here we have the the product from the CT times CT and OT. So in this case we have now the ST equal to OT multiplied with the times CT, and you see the output here can be understand as the gate, saying that how much the output will be produced and will be transferred to the next step, right? If the OT here, because of the sigmoid function, if the OT equal to 0, then of course the ST will be 0, saying that okay, the cell state at this step will produce nothing for the next step. Okay, so if the OT here equal to 1, then okay, the highest step at this step ST will be output fully to the next step. Okay, now we have a specific gate, another component of the LSTM, the forget gate. The forget gate also accepts the input XT and ST minus 1, and it has the weight matrix WF, and it is a formulation for FT. It's a sigmoid over the net input, right? And for that you use in combination with the CT, and now the CT is equal to FT multiplied with CT minus 1 plus ET multiplied with CT. So the ET here is the input gate that say how much the input signal will be used to compute the current C state, the cell state accepting. So step the FT here will be used as the gate, saying how much signal from the previous cell state CT minus 1 will be used to calculate the CT. If the FT equal to 0, then the computation for the CT had nothing to do with the CT minus 1, right? So in that case, it totally forget the cell state of the previous state, and it calculates the cell state just from the current input, right? In the case of FT equal to 1, then the computation for CT will take fully the CT minus 1 and then IT multiplied with CT. Okay. Okay. So in the forward pass, this is all the formulation for LSTM cell. We have the ZT, IT, FT, OT. This is for the input. This is the input gate, forget gate, output gate. Okay. And this part is for normal INN, right? And we have different weight for different gate, input gate, forget gate, output gate, and this is a normal vanilla INN, and the input is XT and ST minus 1. Okay, this is CT, this is ST, right? And that was for the forward pass. And now the back propagation pass in LSTM. Sorry, I need a few minutes. Okay, so now we discuss the backward pass in LSTM. We can see that for the gradient from CT to CT minus 1, right, the gradient is propagated back only through element by element multiplication, the pairwise multiplication, right, and not through matrix multiplication and time function, right. This is the computation of CT. You see the back propagation from CT to CT minus 1 is that the pairwise multiplication, right. And in the vanilla RNN implementation, you have the hidden state equal to the time function of the weight and then the input, and that part will make vanishing gradient for further step backward, right. So in this case for LSTM, we have the senior from CT to CT minus 1 is only back is propagated back only to element by element multiplication, not through matrix and time function. So you see that we can reduce the vanishing gradient effect, right? Okay. Okay, so here's a question to discuss. Do LSTM solve the vanishing gradient problem? The thing is that architecture make it easier for the INN to preserve the information over many steps, because the computation for the state of step CT backward to CT minus 1, the previous step, have nothing to do with the matrix multiplication and times, so that the senior can be somehow easier to keep, right? For example, if the f equal to 1 and the I equal to 0, then the information of that cell is preserved indefinitely. F equal to 1 and I equal to 0, then the CT will equal to CT minus 1. So no information is lost, right? By contrast, it is harder for vanilla RNN to learn a recurrent weight matrix WH that preserve information in hidden state, because we always have the hidden state equal to time of WH and then the input, right? And the time function make the output to be in small range from -1 to 1, right? Of course, the LSTM does not guarantee that there is no vanishing or exploding gradient, but it does provide an easier way for the model to learn long-distance dependency, right? So that's the conclusion for us. We have other variation, namely gate recurrent unit, ZRU. In the ZRU cell, they do not use separate cell states, but they combine it with the hidden state. And they also combine the forget and output port into the update port. And this is the configuration for the ZRU unit. You have this is the input X, input hidden state step T minus 1, and you have the reset gate to say that how much the information from previous hidden state will be accessed for the computation of the current state. And then you have the update gate saying how much information from the current computation will be update. How to say? Is it update? That's it. Yes, it's update because you have the direct connection from ST-1 to that join computation. Okay, so here's the formulation for ZRU unit. It is RT Okay, nothing special. This is a ST prime. Okay, this is nothing special. And now we have the ZT, the update gate, and then you see you have the ST equal to 1 minus ZT multiplied with ST minus 1 plus ZT multiplied with ST prime. Of course, so in this case, it's update because it use the ST minus 1 directly in the formulation, right? How much you update from the previous ST minus 1. Right, how much you update from ST minus 1. Okay, so you may have multi-layer INN as a multi-layer feed-forward neural network, like this way. This is the first layer, INN layer, and then you can have stack another INN layer on top of it, and another one, and another one. And then you got the output at, a stack of INN. And you also can have bidirectional INN. In our previous example, we only have one directional INN going from left to right, but assume that you want INN to be from right to left also, then you can design this way. The first hidden layer is for the direction from left to right, and then you also have the weight for the right to left, right? And this architecture is so popular in sound recognition, because for sound recognition, you are seeing that the information at the current step is affected not only by the previous step, but also, the step forward, right? Any questions so far?
I have a question.
Yes.
Why do we use tanish function and sigmoid function for this structure after we said a lot about the bad things of those functions?
Yes. So the LSTM cell was presented quite a long time ago. For example, it was presented in 1997, and before that, people always working with the neuron with the small size, and they mostly use the sigmoid and time function. What I am showing here is the LSTM design at that time. However, if you are seeing the configuration of the LSTM cell, you are seeing the design is to be very specific with a very specific gate, and of course for the gate is for the gate you want to have a way to control how much the output will be passed through the gate, right? And for the gate, saying that you can open the gate entirely, so to let the information can flow entirely to the gate, or you can close entirely. So the gate could be a function, could be any function that can produce a value from 0 to 1. So in that case, of course, the sigma function will be the best candidate for using as a gate, right? And the time function here is normal RNN, would use for the times. Of course, I think that you might try to not use the time function in here, but for the gate, I think that you might use the sigmoid, or you can use other function, but to make sure that the output to be designed from 0 to 1 to keep the semantic of that configuration. Otherwise, it could be a network, but you cannot name it input gate, output gate, and forget gate. Is it clear for you?
Yes, it is. Thank you.
Any other question? Okay, we need to discuss some application? Okay, this part would be quick, so let's continue. And an application in sequence classification problem. Okay, we can have a sequence variable size input, and we fetch the input into RNN, and then we use the last hidden state output, and using that last hidden state output to be fed to the linear classifier layer, and then we can have the prediction here, so that in this case we can ignore every intermediate output, right? In other configuration, we may say that the intermediate output have also some meaning, so we can decide to just combine the hidden state of every step, and then we do the classification over the combination of the hidden state. It's still okay, right? We may say that in that normal INN, the relationship is in left to right direction, and in some case, for example, in text processing, when we want to detect the entity of the text, for example, name entity localization problem, we may believe that the label for specific word token is affected by not only the word before but also the word after in a window, for example. And in that case, we might think a bi-directional INN would be helpful, right? Here's the example of training character INN after different number of iteration. This is after 1000 iteration, very small number of steps. Then you see the model cannot learn anything. It's that output a random sequence with no meaning. And then it is output after 300 iteration. Okay, it already can predict, some meaning word, right? And then when we are at 700 iteration, you see, they can predict the correct some correct phrase, right? And then it's more than 2000 iteration, it can predict the correct sentence, right? Okay, this is the image caption generation, something like that discussed with you in the beginning of the lesson. So I think that I don't need to explain more about this, right? And this is the result of the image caption generation model. It looks really promising. I see there's some experimentation with this model that, for example, that would be helpful for vision impaired people. If they lost the vision, then we can have a device that capture the surround environment, and then that image will be used to fed into the image caption generation, and then it can how to say, we can use some model such as a text-to-speech model, so that we can play the sound, and then the vision impaired people can know what is in front, and then they can, change the direction if needed, right? For neural machine translation, a lot of work have been applied the second RNN to machine translation, and they get good result, good performance for this. Here is a second-to-second model, and in that model we are actually using two RNN. The first RNN is like the encoder that encode the source sentence into latent space, I mean multi-dimensional space, and then from that latent multi-dimensional space, we have another decoder that generates the sentence in the target language, right? And there are two papers that you can read about neural machine translation with a second-to-second model. Some references you can read and study more to get more idea about INN. I mean, CS231, for example. Yes. Okay, so I think that we can have break of 5 minutes, and then we will continue with the practice a little bit. Okay, so I have two labs for you. The first one is about recurrent neural network and LSTM, sorry. And we have another lab about basic implementation of neural network. It's up to you. If you already understand PyTorch and you have some experience with PyTorch, then you can start directly with the notebook of RNN. If not, then you might start with the second notebook about, some basic introduction to neural network. Is that clear for you? Okay, you may clone the lab and work on Colab or on your computer. Okay, so I will give you alone for 20 minutes, for example, and I will be back to see how far you are going. Okay? Hello. So how are you doing? Hello. Okay, good. How about the other? Okay, so I will ask one of you to show the notebook and discuss about it about for everybody. All right, so let's see. Nguyễn Hoàng Nhật Quang. Nguyễn Hoàng Nhật Quang. Okay, so I will mark that you are not in the class for today. Phạm Thanh Hưng. Phạm Thanh Hưng.
Here.
Okay, so show your notebook and discuss about it.
Okay. You see my notebook?
Oh, so you are not in your computer, but you are in Team Mobile. Okay, so I will ask another one to share the notebook. Trần Quốc Lập.
Here I am.
Okay.
Wait for me for a second. Do you see my screen? Do you see my screen?
Yes.
I have just finished the gradient clipping.
Is there anything to discuss about the notebook?
No.
Okay. So maybe we should stop the lesson for today. I really expect that you guys spend time on working on the notebook so that you can get experience for that. Okay, so thank you for the attention and see you in the next week.